Okay, so welcome everyone to our colloquium here in ICAT. So today we have Professor Iltai Isaac Kim, if I pronounce that correctly. Dr. Kim is an associate professor at Texas A&M University-Corpus Christi. He specializes in optical diagnostics and thermal fluid applications in near-surface phenomena, including evaporation, boiling, and wetting, with expertise in advanced optical diagnostics, such as surface plasmon resonance, interference fringe, and aperture total internal reflection. Dr. Kim has collaborated with the prestigious U.S. Department of Energy, laboratories including Sandia and Argonne National Laboratories. Currently, he's a PI in the National Science Foundation, NSF, and the Department of Energy Office and Science, Basic Energy Science, where he explored nanoscale liquid film dynamics, in-phase change, heat transfer, and investigate the enhanced mechanism of plasmonic photocatalyst in water splitting, respectively. So we welcome Professor Kim.
Yeah, thank you very much for inviting me today, especially for Dr. August and the Agnes and everyone. Yeah. Today, I'll talk to you about my lab's the most recent research achievement about droplet characterizations based on the optical diagnostics, such as interference of fringe techniques and aperture total internal refraction technique. Okay, and the bottoms and my funding agencies currently. My research collaboration so far is with universities and national laboratories and industries. Yeah. My lab has the two main research directions. One is nanochemical imaging area, and the other one is about energy conversion. This one is the most recent result, and now today I'm going to talk to you mostly about the bottom three areas. And now here, this one the center one shows ultra thin nanoscale liquid film characterization with surface plasmon resonance imaging. Okay. And also this one shows, micro droplet characterization. Using the aperture total internal refraction technique. For this one shows fingerprinting microscope. This is another view I have done in my the former period using based on the surface plasmon resonance imaging. For example, one is about mixing phenomena, and the other one is cell line solution mixing kinetics, and this one is thermal energy detection with surface plasmon resonance imaging, and the one is evaporating droplet self-assembly, and the other one is unveiling hidden cavity formation during the self-assembly process, and the one is to show surface hydrophobicity caused by a self-assembly process. And this one shows the other research effort from my research career about energy conversion. For example, I think some of you are doing this kind of research, right, based on the nanophotonics. I did work on the epsilon neo zero and hyperbolic metamaterials and perfect absorption, and also related with the metal nanoparticle induced absorption increase. So now today, I'll talk to you about three topics. One is about refraction interference fringe technique for dual droplet profile structure, and secondly is about transmission interference fringe techniques for the dynamic evaporation process, and lastly aperture total internal refraction, shortly ATIR, for droplet characterization. Okay, And here, I mean, originally I thought about including another one, cost about comprehensive interference fringe technique, but looks like, I mean, it's not officially, granted to publish yet. So I drop it, yeah, just in case. Yeah. So let's amend I talk to you about refraction interference fringe techniques for dual, profiles of droplet. Okay, this is one. This I mean the published I mean the last year. Now I mean our configurations based on the this total internal configuration is I mean it looks very bulky one, right? Bulky structure, and we use this one, and then lasers are shining on, and we are using the equilateral prism, right? And the sample is on the top. Actually, this one is the same one. I mean, which is now installed in the Dr. Augusto's lab. Now, I mean, the reason why I mean we are talking about this one is because I mean, when we do experiment, we observed, some weird, phenomena. It's not weird, some the unexplained phenomena. Like I mean, firstly, as you see on the left side, we I mean observed these fringe patterns on the far field screen. Okay. And for the oleophobic cooling condition, that means the thickness is very thin. It's not a monolayer, but the droplet is very thin. We observed this phenomenon, and then we also observed there is no fringe patterns for the very thick droplet. So we come to have a question about why we have this kind of far field interference fringes. And then we thought the main observation we have here is this far field interference fringe is caused by dual interference dual droplet profiles, not just convex profile. If you have a convex profile, and then the beam would be just expanded without any interference fringes. That's why that's the main the focus of this research here. So we analyzed why we have interference fringes from the far field, and the other characteristics. So now we are on the go. We conducted geometric modeling for the fringe generations, right? And also we calculated the optical path difference between the convex and the apex, reflected rays, and the edge regions reflected rays. We on the go geometric modeling, and then we show that each optical path is function of the fringe numbers. How many fringes we have. Actually, this relation is pretty similar to the small scale phasor interferometry, relation. Okay. And now this slide shows the other geometric modeling between the contact angle. Contact angle is the angle, right? The measured in the inflection point of the droplet, right? And then now this slide shows the relation geometric modeling between the contact angle and the fringe radius. Fringe radius means from the center, from the expanded laser center and to the edge. That is a fringe radius. We defined this one, okay, and then we got a relation between the fringe radius and the contact angle here. Contact angle is now is in the equation. This result means well, by the way, I didn't talk to you the background of contact angle here. I think most of you are from electrical engineering and also physics. Oh, yeah. Contact angle is one of the most important properties, right, in determining, surface materials, surface energy, for example. And then contact angle is, is very, the substantial one, determining the surface wetting and other surface phenomena, including evaporation and boiling, and the cell substrate adhesion. That's why we are, we are doing this kind of research here. Well, by the way, here the reason why we undergo this kind of geometry modeling is because to measure contact angle, we found out that if we could measure fringe radius, and then we can determine the contact angle, rather than the directly measuring or also without requiring the microscope. Okay, that is purpose of this work here. So this one shows the relation between the again is a kind of a summary between the OPD and the fringe numbers. We got this simple relation. This one is from the previous this geometric modeling, and also we showed that by other geometric relation derivation. Okay. And then here Fn is the fringe numbers, right? And lambda is the wavelengths. And also we've got this relation correlating the contact angle and fringe radius. Now here this relation shows the fringe radius as function of contact angle here. Yeah. So it's not shown here, but theta TRN PA is a function of contact angle. Okay. This one means we can determine, right? Determine the determine the optical phase difference, and also we can determine the thickness, actually, drumless thickness, and also we can determine the drumless contact angle by measuring fringe radius and fringe numbers, respectively, analytically. And then to prove this one, we undergo ray tracing simulation by following these flow steps. And this is one the ray tracing result. This one shows a very simple, the schematic, and this one is comparing the comparison between the real interference fringes and each analyzed result. Now here the white one is from the intensity read from the real photo, and the red one, the green one is a simulation. They shows the good result each other. This one is ray tracing result. And now we showed that this result for the three cases, non-coating, oleophilic, and oleophobic coatings. Simply very thin drumlet, right? Kind of a thick one and very thick one. Okay, and with the different incidence angles. Okay, we verified it, and then here we show that we counted the fringe numbers and the fringe radius, right? And this is experiment, and this one is the ray tracing simulation for the non-coating and the hydrophilic coating. Well, by the way, we don't have any fringe formation for the oleophobic coating, for the thick coating. Okay, and this one shows another result. And now this table shows the ray tracing related simulation parameters for drumless dual profile. For the, it's not shown, I mean, here, but I mean, this one, this one is, I mean, the simulation result. Okay, let me, I mean, quickly go to the original one here. Yeah, this, I mean, drumlet, this figure has, I mean, a lot of interesting one, because, I mean, I'm sorry about the kind of shifted figure. Now here, this one shows, I mean, the precursor film thickness. Precursor film thickness is very thin one. It's usually known as, I mean, below 100 nanometer. It's very thin region, and also it's very difficult to measure using, I mean, the established metrology techniques. Okay, and now, and also here, this one is, I mean, the height, from the height, right? And the radius is from the center to the edge area, and also this one, the I mean, the left and right is symmetry. Okay, and this one shows convex profile and the concave profile for the center, inner, and outer region. Okay. Well, but another one, I mean, I want to tell you is in drumlet profiles, it's very unclear about a drumlet has a dual profile or single profiles. I mean, when we talk about a very large scale drumlet, it's not a big deal, right? But we are not talking about very thin, very small drumlet, right? And then the profile determination is going to be very, very challenging, because, I mean, the generally known technique is very, I mean, it has, I mean, limitations in the resolution. Okay, if you use a side view imaging, firstly, okay, and then the other one is we have to use generally to see a very, I mean, small scale contact angle, we have to use microscope. But a microscope has limitations of, we cannot see very large, diameter drumlet. Okay, microscope is very, very, I mean, the limit, right? Because, I mean, microscope is very designed for imaging in small scale. But when you talk about a large scale drumlet, like a few millimeter, it's very challenging. However, if you use this simple, configuration like reflection interference or transmission interference, we can, I mean, characterize regardless of, drumlet sizes. Okay. Yeah. Now, I mean, this one, back to here, the table shows a very reasonable, drumlet profile related parameters. Here, it shows, I mean, contact angle, number of fringes, comparing the simulation and observation. It's not, I mean, perfectly same, but it shows a very reasonable, matching each other. Okay. And also the other one I want to tell you is, I mean, we used the hyperbolic profile structure for the outness here. We used to here in the calculation, we used, I mean, the hyperbola profile. Actually, I mean, this is, I mean, it's a still open question. We don't know whether it is hyperbola scale or parabola. There's no, I mean, experimental evidence still. We now at this point we are now guessing the profile would be hyperbola, and then we got a very, I mean, reasonable result compared with very reasonable result from the experiment and simulation. Okay. And now, I mean, from this result, we also obtained the other interesting result, like a precursor thickness. It shows, I mean, they are below 100 nanometer. Okay, and this is also, I mean, the simulation result. And also, I mean, the inflection point is usually located between the less than 10% of, the droplet radius, okay? Now this result shows, the droplet, thickness and versus the fringe numbers. Now it shows a very, perfectly, matching result each other between the observation, geometrical formulation, and ray tracing. Now, we can see it can be shown as a linear equation. Okay, the experiment result shows, almost 99.7% between the experiment and the theory. Now this one shows contact angle variation versus fringe radius. It also shows a very good result. You may wonder why each data point is scattered, but actually the important thing is the matching between the experiment, geometry formulation, and ray tracing for each data. For each data, they are very nicely matching each other. Okay. And also this one shows a similar result with some contact angle contour. So from this research, lesson 1, we showed that we successfully showed that the droplet could have dual profiles like concave and convex, not just convex profile for the very thin droplets. And also we showed that each relation is like the phasor interference thickness relation. Okay, and we also showed that each contact angles can be measured by the fringe radius determination, and also this technique is very good for very small contact angle, less than 5 degrees. Okay, this is now my first talk. Let's move to the second talk of my, presentation. Now it's about, based on this refraction configuration, we studied more for the transmission, configuration. Actually, the reason why we started from the refraction is because it's like, it's very similar to total internal refraction configuration, right? We just started there, and then we expanded the configuration to the transmission, right? And then we did it for the we did it for the droplet evaporation dynamics, and then we explored these transmission characteristics, and we also observed that evaporating droplets is going to change its profiles from the convex to the dual convex concave during its evaporation process. And also we observed that the contact angle increases at the end of dry out, which is very interesting phenomena, and from the physics point of view. Okay. Now let's see. Now this is the transmission, right? We designed this one as the rectangle, original refraction configuration to the transmission. Okay. It's again, it's kind of bulky style, bulky dimension, and now it shows some substrate, microscope images, and the bottom one shows side view images and its corresponding, TIF transparent interference fringes. Now here, these two images they are corresponding each other for the same, sample. Okay. Now here, this one shows 10 degree. Here, angle is the apparent contact angle measured from the edge. This contact angle is like macro. It's called as a macro or contact angle. Okay, and now here it shows that with the increasing contact angle, this one is a side view images. It's very clear, right? It's very clear to measure contact angle. Or by the way, transmission fringes shows each proportional increase. For example, 20, 40, and 87 with different contact angles. Okay. Now this one shows is the geometric schematic for the we call it as TIF, transmission interference fringes. Laser is coming, right, and then the shining is passing through the top the screen. Okay. And we also here we put the expander to make laser light to bigger scale to cover whole drumness. Now this one shows one example of the geometric formulation for the contact angle and the fringe radius. Now this one, here we conducted a comparison between the transmission configuration and the refraction configuration. Now here, transmission configuration shows the wider contact angle measurement. That means the transmission would be better in the wider contact angle measurement. However, also if you see, if you focus on the small contact angle, the refraction may be better. Right? Refraction can provide a better resolution. Now this one shows the contact angle determination depending on the different instance angles between the simulation and experiment. Right? This one shows up to 0 to 90 degree, and the right one shows a zoom view for the smaller area here. Okay, it shows the good agreement each other. Now this one shows we also investigated transmission interference in terms of drumlet liquid refractive index. We used the calibrated index from the 1.3 to 1.73 from the Kajil labs, and it shows very good agreement each other. Simulation and the experiment. Okay. Now this one shows time series of evaporating drumness images. Okay, the top one is top interference fringes, and the middle one is side view. Middle one is the top view, and the most bottom is side view images. It shows relevant reasonable change with time. Well, by the way, we see at the end of dry out, we see the fringe radius increases, which is not expected. Okay, we will see later, and then the 5 or 40 seconds, all the drumness evaporated. Here the liquid is water, pure water. Okay, and now also it shows us some constant radius evaporation. It's the scale is kind of a big one. It's individual cellular drumlet. So now here, this image is to show, this time 5-20 seconds here. The reason is because experiment results shows that fringe radius increases. So increasing fringe radius means each contact angle here, the left side here, contact angle increasing. Okay, this observation shows that the evaporating drumness, evaporating flux distribution is not uniform along the evaporating drumlet, along the each surface. Okay, that causes this fringe radius increase, and also correspondingly, contact angle increase at the end of dry out, which is now thought to be caused by non-uniform evaporation flux, which is not analyzed in detail yet, okay? Which is which need to be studied further, okay? And the other one is, the other interesting point is here, we observe that it's not that clear from the screen, but we observe that the fringe, the interference image is going to show fringe pattern at the end of, at this time, okay? Interference fringe. Previously, it doesn't show, just an expanded beam. Expanded beam means it's, the drumlet profile is a convex structure. However, at this time, the drumlet is going to show at least dual profile. That's why we have a fringe is formed. That is also the pretty interesting result. Which is which which need to be studied further. Why drumlets will change its profile. Well, but again, the one thing I want to mention is that at this region, right, drumlet height is kind of a large one, but at this here, the thickness is very thin, like less than 1 micron, and the contact angle is also less than 1 degree. This range is very challenging with the existing metrology techniques to characterize. So here, in this the work, we show that the TIF can successfully characterize evaporating drumlets dynamics, and also we did TIF characterization parametric study for the incidence angles and the drumlets refractive index. And also we showed that TIF is better than the RIF in terms of wider in terms of contact angle detectable ranges. And also as I talked to you earlier, just ago, TIF is very effective to determine the evaporating drumlets profile change, convex only to the convex concave profile. Okay? And also we observe that contact angle it doesn't keep increasing. Okay, contact angle looks to keep decreasing, right? However, we observe that is increasing at the final stage, which is not reported yet, which is still an open question in this drumlet, microfluidics society. Why the contact angle shows increasing phenomena? The reason is because here, this is now constant radius evaporation. So that I think that is the main reason why it shows contact angle increase at the end of dry out, which is first reported here in this society. Okay. And also here, I want to mention is another result is for integrated or comprehensive interference fringe techniques. Now recently we showed that this interference fringe techniques can be applied to to detect very small nanoscale thickness film thickness measurement, like the less than 100 nanometer. In general, very simple schematics. Okay. Actually, this result is, we showed that by, up to now, so far, we showed that by simulations, but pretty soon, we have a chance to verify it from experiment. Actually, 100 nanometer thickness is very, challenging, the thickness. Okay. But now, this interference fringe far field shows this one can be a very, effective optical techniques. And also, the reason why this is important is because, this range, the contact angle is very small. Okay, it's around 0.001 degree. if we, convert it into radian, it's less than 2 microradians. It's very, very small, small angles. Okay. Well, by the way, to achieve this one, we need to increase the walking distance up to 3 meters. 3 meters is kind of long distance, right? So we are now trying to find some, we want to extend it to our laboratory space. Okay, this is second one. I think I have more time, right? Yes. Yeah. Now I want to talk about the aperture total internal refraction, called as ATIR. Okay. And this one is also meant to measure, the lower contact angles less than 5 degrees. Okay. Now the ATIR is pretty similar to the previously talked to, refraction interference of fringe setup. Yes, it's a similar one. Okay. Well, by the way, we put a detector here, which is also very similar to Dr. Augusto's, laboratory setup. But we put the detector, but also we put some aperture with a different, radius. Okay, and then we made some, microarray using some PDMS stamp to control the sample. This is a photo of the optical setup. And here, in this case, we analyzed a drumless refraction, okay, into 3, kinds. One is, glass air interface, and the other one is glass drumlet interface refraction, and third one is the refraction from the drumlet and the air interface. We categorize refraction into 3 categorized. Okay, and then here we intentionally put the aperture to investigate each effect. In other words, with the adjusting aperture size, we can control the, for example, the refraction from the drumlet surface, right? Because if we have a drumlet surface refraction has a too high refraction, and then it will be detected from it will be captured in the detector. Okay, that's the principle of this technique. Okay, and also we introduced the effective refraction zone, and also we showed some also confirmed some Kuss-Haken shift effect. Yeah, we follow them, as you know. We follow we use some Fresnel equations, right? We as said again, we the category classified refraction as 1 to 3. Okay, and we formulated like this. Okay. Now this one shows the reflectance depending on the the incidence angles. Okay, and then we describe each different reflectance 1 to 3 for the different incidence angles. Okay. For example, for small angles, right? And then we can capture all reflectance: glass air interface, glass liquid interface, and the liquid air interface. However, with increasing incidence angles, sorry, I'm sorry about that. In the very small angles, we cannot detect the reflection is not captured to the detector. However, with increasing incidence angles, we capture only the reflection from the glass air, and then with more increased angle, we can detect, the glass and the liquid interface refraction. And we made we had a simulation for the multi array of drumlets. This one shows, I mean, the laser droplet, because you know what, I mean, we expanded the laser light in a bigger diameter, okay? So laser light is, I mean, can cover large area, okay? And then we got this kind of, this kind of the calculation for the different incidence angles, right? And we also calculated the reflection lengths and each corresponding area and some each relevant factor. Okay. Now this one shows the schematic of 3D ray tracing modeling. Okay, and we as you know, I mean, we put a aperture in front of detector, right? If we zoom in here, and then we can see the reflection 1, 2, 3. They are all collected here. Well, by the way, if you aperture is small, right, and then the some part of reflection from the refraction from the glass and from the liquid and air, they would not capture it here. Okay, but this is the formulation for the 3D ray tracing modeling. Okay, this is some procedure flow chart. Now this one shows beam profile for the to do our experiment. Now here this is the real experiment. This is an expanded beam. You know what? Another one is here. The droplet is droplet. They have all convex profile. Okay, they don't show any fringe. Okay, they all show continuous expanded light. Okay, and of course the droplet's contact angle is kind of big one, like a 12 degree. Okay, we don't see any the interference fringes, and then the upper one is our experiment and the lower one is a simulation. They show they are matching well depending on the different incidence angles. Okay, we this one shows intensity depending on horizontal position and it's a vertical position for the imaging out of the imaging analysis. As you see here, this drum is very big one, like the 339 micron. It's kind of a big one, yeah. And then we go through the reflectance measurement like P and S, P polarization and S polarization, for the controlled micro droplet patterns. And here we use the oil rather than the volatile liquid. Okay, oil is they are not volatile, right? So it's much easier to characterize. We intentionally make this kind of droplet array from PDMS stamping method, and now it shows very the good agreement between the symbol is experiment. Okay, the line is simulation. They shows a very good agreement each other. And now this one shows we verified this result depending on different aperture sizes. We tested the 3 different apertures, 1 to 4 millimeter. It's in diameter. Okay, and also we are on the go P and S polarization for each measurement. It's manual the measurement, and it shows very very reliable match between the experiment and the theory. Okay, this one is the single individual droplet. Okay, and also the bottom one shows the simulation only from the refraction from the liquid and air interface, because liquid air interface at some point this one is the theoretical one, but also we can get a result from the other aperture sizes. Okay. Also, we explored working distance effect for the reflectance measured on the detector. Okay. We tested different working distance from, for example, 50, 75, 100, and 150. Okay. And this one is total reflectance, and this one is individual reflectance. 1, 2, 3. Yeah, this one shows the result for the very big scale droplet and the small scale droplet, macro and micro, with the different sizes of apertures, and also with different working distance. Because we are now testing the aperture effect, that's why we are testing different working distance. It's very it's very tedious measurement. Yeah. And now this one shows the geometric modeling for the effective area, okay, to the reflectance, okay. Yeah, this one shows the reflectance ratio of the liquid glass, liquid air interface, and the total reflectance depending on the different aperture sizes. These are simulation. Yeah. This one shows the area ratio and the intensity flux ratio, okay, for the different aperture sizes. Okay. Now this slide shows the relations, how to determine the droplet height from out of this ATIR measurement. Okay. And now this one shows a result, droplet thickness measurement. Now it shows 2.4 micron thickness, right? And the red one is the thickness estimation by phase or interferometry, and then the symbols experimental result. It shows a very reasonable, very good the agreement, right? Compared with the phase interferometry measurement, 2.4 micron thickness determination from the different aperture sizes, 2, 4, 1, 2, 3, 1, 2, 4 millimeter, sizes apertures. Now this one shows again the droplet thickness measurement for the micro droplet, like the diameter is less than 250 micron, and for the macro droplet, like radius is larger than 3 millimeter. It's very different scale, right? Around the 10-fold. We show the very reasonable, very good result between the ATR and the phase interferometry measurement. In the small scale, right? In the small scale droplet, it's very difficult to measure contact angle using the side view. Side view is effective on the in big scale, right? When we try to measure a very small scale droplet, we have to use interferometry technique by counting the number of fringes. Okay. Now this one shows there. Okay. Yeah, this one shows again the contact angle distribution, right? The small area and the large contact angle droplets. Okay. The ATR is very also a very effective one. Okay. I'm sorry about this type. Yeah, one. This one shows the contact angle determination depending on the incidence angles for the different, droplet height. These are the simulations, but this one shows the ATR can measure up to almost 90 degree of droplets. Yeah. This one shows again the same one. Yeah. Now here, this one shows the fingerprinting's micro droplet feature size. Yeah. Because of this research is originated from this one. Originally we want to characterize fingerprinting effect. Okay. And this the reason 1, 2, 3 talks 1, 2, 3 research is originated from this initial study. Okay, this one shows reflectance versus coverage fraction. Actually, this result is we used real fingerprinting. Real fingerprinting characterization is very challenging. It's very complicated. Yeah. So we did reflection, transmission ATIR. So now we are about to combine SPR and the interference fringe and ATR techniques. Okay. This is the SPR result from the ultra-thin film sequence measurement. We conducted SPR measurement and to show that liquid film thickness can be measured with 2.5 nanometer actual resolution. Okay, feasible resolution is 2.5 millimeter. It's very the interesting result because the SPR is the kind of very simple one, but its sensitivity is a lot. Yeah. This is the stress distribution using the SPR depending on different stress. Yeah, this is the PDMS films optical and mechanical property detection caused by punched indentation. Yeah. This is my first generation SPR setup. Yeah. And this one shows SPR's initial work the mixing phenomena. SPR can detect mixing phenomena very easy way. Okay. I want to start my talk now. Okay. So thank you for listening to my talk. Yeah. Thank you.
Thank you very much, Professor Kim. Does anyone have questions?
Hi, sorry, can you use these techniques for other types of substrates? For example, not just flat substrates, but also curved, like for measuring contact angles when you have pillars.
Oh, the structure pattern, right?
Sorry?
Are you talking about structured pattern, pillar?
Yeah.
Yeah.
Well, not just structure, but also when you have pillars. For example, it's difficult to measure the contact angle when you have a pillar, a drop on a pillar.
Yeah, pillar case, that is not, the easy situation, right? But I think, with some calibration, I think we can also apply it into the pillar, the structured pattern surface, yeah. But we need, some calibration, yeah, definitely, yeah. So one work is we are trying to do is we are not trying to do characterize micro or nano structured surfaces. Yeah.
Mm-hmm.
Yeah.
And for that, you can measure the contact angles for structured substrates.
Yeah, we want to try. Yeah.
Okay. Yeah, and another question: what is it that limits that you cannot go below 5 degrees?
Oh yeah. So here let's talk to the initially about the interference fringe techniques, right? We came below the confound one is now. Yes, it can detect less than 2 microradians.
But why you cannot go below that?
Actually, I mean, we can go below, yeah, with, I mean, the extended walking distance. Technically,
Okay.
yeah, we can,
Ah,
yeah.
okay, so the limit right now is just that you need this setup to
Yeah,
reach
I
that.
guess, I mean, the only limit is physical space, I think, yeah. If you have a very strong light source, yeah, we may, I mean, able to measure maybe 10 nanometer scale, thickness and smaller contact angle, yes, yeah. Yeah, that's a very good question, yeah.
Can I ask another one? Can you infer? I mean, in your draws, you draw the precursor film.
Precursor film, yes.
Yeah. With an angle at the end, but in many cases, it is assumed that the contact angle is 0.
Oh, yeah.
Can you get some information about this? Because I assume that these are just assumptions of how is the precursor film. Can you infer how is the form? Well, what is the profile of the precursor film?
Yeah, there's some, and my understanding is that is now still open question in the society. Yeah, yeah. Because I mean, what I want to do is, I want to explore. Yeah, explore. I mean, very thin, precursor film regions using the interference fringe and also surface plasmon resonance imaging techniques. Yeah, yeah. That's very good question, but still, very open,
Yeah,
area.
very open.
Yeah,
Okay.
yeah.
Yeah, thanks.
Yeah, thank you. Yeah.
Anyone else has a question? So maybe.
Yes, very nice talk. Very impressive how the simulations and measurements coincide each other. Very complicated measurements and simulations. But all the simulations are based on ray optics, right? What is there a limit, like the size of the droplet? Can it go, what's the smallest size, let's say diameter of the droplet that you might have to take into account maybe diffraction of light as it gets reflected from the droplets? Is there any limit that you have seen that the simulations do not match? If the droplet is very small, will there be a problem with the simulations or not that you know of?
Yeah, actually, I mean, that's very good questions. The smallest droplet we try so far is maybe, I mean, the 10 micron.
10 microns?
10 micron, yeah, something like that.
Quite small, yes.
Yeah, we didn't go below that, yeah. Yeah.
Okay. Okay.
Yeah, we may try, I mean, the narrow droplet, but one, I mean, obstacle, I think is maybe diffraction limit related one.
Okay.
If the droplet is too small, right? And the light has a diffraction limit issue. So yeah, I think that there may be
maybe diffraction might start
yes,
to
yeah,
affect
yeah,
if you go below 10 microns, maybe. Okay.
But 10 micron is fine. Yeah, I think that we tested it 10 micron. Yeah.
10 microns.
Mm-hmm.
Okay.
Yeah.
Very interesting.
Yeah.
Now I was so interested in these graphs you showed about reflectance versus the angle of incidence. And you can see there at least 2 critical angles at some point, no?
Mm-hmm. Yeah.
What can you measure from those curves, or what are you measuring from those curves?
Oh, we want to confirm our technique is following Fresnel equations. Yeah.
Oh, okay.
We want to confirm. Yeah.
You are okay. Just checking
Yeah.
there.
We want to verify our proposed model.
Okay.
Yeah. Because we characterized reflectance into 3 kinds, right? We want to check that is correct or not. Yeah. That's why we went through, so many instance angle ranges and the PNS with the different, sizes. Yeah.
Okay.
Mm-hmm.
Because I guess in some of the curves you showed, it appears as if you can see two critical angles, right?
Mm-hmm.
One with air, the other one, I guess, with the droplet.
Yeah, yeah.
So can you measure the refractive index of the droplet itself? Yes.
Index of droplet?
Of the droplet.
Oh, yeah. So, I mean, if you use some and interference fringe techniques, right? I mean, you see here, maybe the following one. In transmission interference fringe techniques, we change them and the liquid RI intentionally, because I mean liquid RI is directly affecting the fringe radius, because I mean light is refracted in proportional to the RI of liquid. Yeah. Mm-hmm. Actually, this one is can be used for unknown liquid refractive index. Yeah, if you could measure fringe radius, and then we can determine the RI of liquid. Yeah. It's, in other words, RI sensor. Yeah. Mm-hmm.
RI sensor, yes.
Yeah. Originally, we proposed it as some RI sensing, but we changed its direction.
Okay.
Yeah.
Okay. Very interesting. I have many other questions, but
Yeah.
I'll ask them later on. Yes.
Okay. Yeah.
Yes.
So anyone else? I have a very easy, simple question. I probably missed it from your talk, but you had drops that when they are evaporating, they decrease the contact angle. So I think that they are pinned to the surface, but you don't say how you treat it. Your surface is to get the drop to pin to the surface.
Yeah, the drum is can be regarded as pinned on the surface. Yes, because that evaporation is like the contact radius evaporation. Yeah, the reason why is the drumlet's liquid has some interaction with the surface, right? They will be pinned on the surface, not changing the
But you didn't make any treatment to the surface.
At the time, we didn't do any treatment, but we believe that maybe some surface impurity from air may affect the glass substrate. Yeah, we guess.
So it's just glass.
Glass. Yeah, we use just glass. Yeah.
Okay.
But the surface treatment is very tricky.
Yeah.
Yeah.
Thank you very much.
Yeah. Thank you.
So we would like to thank Professor Kim for this talk. And ¿tenemos un anuncio arriba? No, ya no. Entonces ya no hay anuncio. Muchas gracias a todos.